Okay, so once hello everyone. So once again, I welcome you all in this lecture. So in the last lecture, lecture number 13, we discuss about the ultrasonic machining process, and in that we discuss about that how the ultrasonic means the how we are using the ultrasonic frequency. Okay, with the and how we are this ultrasonic frequency is transferred to the tool or in between workpiece and the tool. We are using the abrasive particles. So how this vibration is transferred through the tool through the abrasive particles, and that will remove the material from the workpiece surface. And one of the important thing about the ultrasonic machining, that is process is applicable only for the brittle material. We cannot use for the ductile material. Okay, in the last in that only we discuss about the material removal rate, as well as we discuss the numerical problems, objective problems that has been asked previously. So that was completed in the last video itself, and in the today's lecture we are going to discuss about the uh, laser beam machining and the electron beam machining. So this is lecture number 14. So let's start. So, guys, here we are discussing about the laser beam machining and the electron beam machining. Here we are not using simply the laser and the electrons. Okay, so here we are using the beam. Okay, so beam means that if like this is a kind of tube, and through which the material is these laser or electrons are coming out, then they should be in a line. Okay, they should follow a continuous line. Okay, so that continuous line we are calling it as a beam. Now if this is related with the laser, then we are calling it as a laser beam. Means the photon that are moving in a path. Okay, so that is a laser beam. And if these electrons are moving in a path, then we are calling it as a electron beam. Okay, guys, till now whatever the in the we started this non-conventional machining process with the chemical machining, electrochemical, and the EDM process, in which we discuss about that how a chemical energy or electrical energy we are using to remove the material. And then we discuss ultrasonic machining and the abrasive jet machining. Okay, so these are the process in which we are using a kind of mechanical energy, we can say. In the abrasive jet, the pressure energy is converted into the kinetic energy, and in the ultrasonic machining, we are using the vibrations to remove the material. Okay, so these are the processes, laser beam and the electron beam, in which if we are here these laser means photons, basically we are calling it as a photons. And in this process, this is electrons which are moving with a very high velocity. It means that we can say this kinetic energy is gained by these electrons on the photons. Okay, and these when these high energy beam with a very high velocity, these electrons, and it has a very high kinetic energy. So when this kinetic energy is retained by this electron and the photons, so they are impinging over the workpiece surface. It is impinging because this beam is impinging here. Okay, it's not like a bombardment. Bombardment means these individual electrons or the individual photons are impinging over the workpiece surface, but it's not like that. Here we are talking about the beam. So this beam is impinging over the workpiece surface, and they are as it has a very high kinetic energy. So this complete kinetic energy is converted into the thermal energy. Okay, now this thermal energy means the temperature is rises, and because of this rise in temperature, the material is melts. Okay, here the temperature which is rises in the range of very high range, we can say like around 10,000 degrees centigrade or more than that. Okay, so if we talk about this like iron or aluminum, then they are generally have a 1534 or 1000 degrees centigrade melting point respectively. So if we are talking about these thermal energy, then this is in the range of 10,000 degrees centigrade. So when these beam will impinge over the workpiece surface, they basically not only melt, they evaporate. Okay, whatever the material that is melted, that evaporates from the workpiece surface. Okay, so is per the aesthetic point of view, whatever the working surface that we are getting, or from the surface finishing point of view, whatever the surface that we are getting, that is quite satisfactory. Means the surface smoothness is quite satisfactory. Okay, so both are basically the thermal beam processes. Okay, Electrical energy is used to generate the high energy electrons if we are talking about the electron beam machining, and the high energy photons are used to generate the electrical energy in case of the laser beam machining. Okay, so how it works, let's discuss it one by one. So first is we are talking about the laser beam. Okay, so first I'm just briefing that what are these elements, then I will discuss what is the working of that. So first of all, this is blue color is basically the vacuum chamber. Okay, here okay, this is a vacuum chamber. Sorry, this is a vacuum chamber. Okay, we are using, and this vacuum chamber is used. Vacuum means the negative pressure that we are creating. Okay, so the negative pressure, generally this process is not we cannot carry out this process in the atmosphere, so that's why we are using it for the we are managing this one into the vacuum only. Okay, so please keep in mind that before going to the machining process we need the vacuum chamber. Okay, so that contains the negative pressure, or we can say, like if I say that is in the range of 10 raised to power minus 4 to 10 raised to power minus 6 torr. Okay, torr is also the unit of the pressure. Okay, that is in converted in terms of the hg, of hg. So you can just look at that conversion. So this is amount of the pressure that used to maintain in the vacuum chamber. Okay, so then we are using the electron gun. Okay, so then it's like electron, after the electron gets, we are using the grid cap. Okay, this red color is the grid cap. Okay, and this line is like that line is there. Okay, so this is a kind of filament. Okay, that filament is basically made of this is a filament, and this is generally made up of either the tungsten, we can say. Okay, or yeah, tungsten we can say, or sometimes it is thoriated as well, means tungsten, that is some amount of the thorium is also added along with that, because a very high temperature is generated, high energy density, these electrons are generated through this, or which provided the path to these electrons. Okay, so this is the filament, and after that we are using the anode. Okay, and one more thing is here that we are connecting with the power supply. So this cathode gun is connected with the sorry, electron gun is connected with the cathode side. Okay, this is the cathode side. Okay, so then it's a anode, and after the anodes it depends that whether we have to use the diaphragm or not, but just for the time being, just understand that there's the diaphragms we are using, and after that we are using the foxing lens. Okay, so foxing lens we also call it as the electromagnetic lenses. Okay, so these are the electromagnetic lens, and after that we are using the workpiece which is mounted over the fixture or anvil, we can say. Okay, so is there is no need to, whatever the material that is melted, there is no need to taken it out separately, because as I said, the temperature which is generating in this process is very high, that is in the range of 10,000 degrees centigrade. So material is automatically evaporated. Okay, now let's discuss the working part of it. So working is like as we are connecting it with the power supply, this electron gun. So this is the cathode side, means negative we can say. So this is generating the electrons. Okay, as it will generate, the purpose of this electron gun is used to only to generate the electrons only. Okay, so this is generating the electrons, and this electron gun is connected with the grid cap. So if you will see the geometry of this grid cap, then it is like a concave shape, means from this side if you will see, then it will be a concave shape. Okay, so concave shape means it's like this kind of things. So whatever the electrons that is generated, they basically try to move in this direction, means electrons always move into the what from where it is generated, perpendicular direction. So what we want is like this, we are not using this grid cap like this, so these electrons will be transferred to this direction. We are using this grid cap like this. So whatever the electrons that is generated, they basically collide with this filament. Okay, means if the electron is generated from this side, this area, then this will generate over, that will collide over this filament. Okay, they will collide with this filament, and this filament is in this direction. So basically it will provide the direction to that in which direction they have to move. Okay, so they will move in this direction, or like this is the filament, or there is a possibility that the ending electrons which is generated at this end portions, they may not collide with this filament, so they can move here and there in other directions. Okay, so to provide them a path, we are using this anode. Okay, now anode, why we are using? Because we are using like anode is a positive. Okay, so these electrons, when it is generated, it will move towards the positive side, so that's why we are using the anode over there. Generally guys, this is looking like there's these two elements are kept like, and we are assuming that these are electrons, but actually this is a periphery, means it's a kind of cylinder. Okay, this is a kind of cylinder in which like first is the grid cap, and bottom of that, we are keeping this anode. Okay, this is this anode is throughout this periphery. Then there is a diaphragm that is also throughout this periphery. So everything in this mention, it's a kind of in try to be considered that is in a cylinder. Okay, circular. So these are the anode. So when these electrons is generated, they moves towards that side, as we are already using the grid cap. So they will provide a filament as well. So they will provide a path to them to in which direction they have to follow. So when these will follow in this direction, they will move over here. Okay. First case, that if they have already make a beam over here, then there may be a possibility that they will again basically they will move opposite from a beam. Okay, then what as I said here, as I said here, that this is a possibility that the electron which is generated from this end portion, because this is not uh, 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 like a curve only. Okay, it's not like a simple like line. Okay, it's like a complete curve. Okay, so how we are keeping uh, the cap over the light to focus in particular direction. So that kind of hemisphere kind of plate is like that. Okay, so if these electrons is not contact with this filament, so they will basically try to move in these directions. Okay, so there is a possibility that they will not make a beam over here at the anode portion. That's why we are using the diaphragm. So what will happen with the what exactly the working of the diaphragm is, they will basically whatever the electrons that is moving apart from their direction, they will basically try to push it. Okay, try to push it and make a beam. Okay, so if the beam is already made over here, then there is no need to use the diaphragm. But if the beam is not made up at the electron, at the sorry at the anode, then it anyhow this beam will become up to the diaphragm. Okay, so the diaphragm is like at we can manage like what is the distance, at the what distance we have to manage, so that we can manage accordingly. Okay, so once now here the beam is done. Okay, now again it will go bend, and means it will move toward downside, and it will move in other directions. Okay, throughout this periphery. Okay, so they will basically try to move like that. Okay, so here we are using the foxing lens, so they will basically come here, and the purpose of the foxing lens is to again the same thing what diaphragm is doing, that we it will try to oppose it. So when it will try to oppose it, basically it will make a beam over here. Okay, it will make a beam over here like this. Okay, so is now there is a, so this beam, when this beam is formed, this beam is collide with this workpiece surface, and as I already discussed that this has a very high kinetic energy. So when it will collide with the workpiece surface, they will complete kinetic energy is converted into the thermal energy, and with a very high temperature is generated. So there will be a evaporation of the material, first melting then evaporation. Okay, so now there is a one question you can ask, that sir, some from the some specific region, like from a specific region we have to remove the material like this one, and when this beam is formed, up to this some amount is removed, like this thickness is covered. So this now when it will move, when it came in contact with this one, with this one, there was a beam, but when it will move towards the downside, again what happened actually here, so they will basically move in this direction. So for that, what we have to do, we have to be means it's already decided that when these foxing lens we are using, at what distance the beam is formed exactly. If this is like 10 mm, up to that the beam is formed, then now it is just assume that this is 2 mm, so now it this distance has become 12 mm. So now there will be a no beam. So what we have to do, we have to move it downward direction 2 mm towards the downside. Okay, means we have to provide a feed mechanism kind of things to the diaphragm. So this 10 mm, this 10 mm distance should be maintained. Why this 10 mm is maintained? As I said, that if this electrons opposed by this focusing lens, and they are making the beam over the workpiece surface. The distance between them is 10 mm. So this we have to maintain this 10 mm. So for that, now again we have to whatever like thickness we have to remove from the workpiece surface, we have to move it accordingly. Okay, so that feeding we have to provide. Okay, so let's see what are the so this is basically the working part of this electron beam. Okay, let's discuss what are the point is there. So EBM process is carried out in the vacuum process. Okay, so vacuum is very important for this one. High energy focused electron beam impinge over the workpiece surface, and that is a whatever the spot size means. For an example, this is a I'm talking about this workpiece surface. So this is a kind of workpiece surface, and they will be, when this beam is kind of, if you will see, then it's a kind of solid, and it's like circular in shape. Okay, so when it will circular in shape, so we can say like this is a beam that is formed over the workpiece surface when you will see from the top view cross section. Okay, so if we see that this what the size of this spot that is formed over the workpiece surface or this cross section, that is in the range of 10 to 100 microns. Okay guys, so this is in the range of 10 to 100 microns. Okay, now, next point is the complete kinetic energy of the electrons, which is moving at very high velocity, is converted into the thermal energy, due to which the melting and the evaporation occurs. That we have already discussed. Okay. So next is what are the parameters that is affiliated with this electron beam machining. So heat source here is the electron gun. Please keep in mind this one. Because of that only the electrons is generated. Vacuum chamber that we are using, so the level of vacuum that is maintained, that is in the range of 10 raised to power minus 4 to 10 raised to power minus 6 torr. Okay, so this torr is nothing but 1 torr is equals to 1 mm of Hg. Hg is mercury. Okay, tungsten filament we are using, so within the electron gun, that should be treated as a, which is electron gun, means this is in the connected with the electron gun only, because this electron gun, grid cap and the filament, that is a single assembly. Okay, that's not these different elements, but single assembly, but different elements are there, but that is in a uh, same assembly. Okay, so it should be considered as a cathode only. Okay, so that is basically the source of the streaming of the electrons. Okay, once the electron is generated from the grid cap, they will basically provide a stream that in which direction they have to follow. Okay, the potential difference that is created, that is in the range of 30 to 175 kilovolt, and the current range that is in the range of 50 to 1000 milliampere. Please keep in mind the voltage here we are using very high and the current is very small. Okay, and the electrons which is traveling in this process, that is in the range of 50,000 to 2 lakh kilometer per hour, sorry, per second. Okay, so this is the velocity. So if this is the velocity, means 2 lakh kilometer per second, it means that, sorry, 2 lakh kilometer per second. So if this is the velocity, then you can assume that how much kinetic energy it has, because that is 1 by 2 half mv square. So this velocity square of that. Okay, so please keep in mind this one. Okay, so this is all about the electron beam machining. Let's move to the next one, that is a laser. Okay, laser beam machining. So first of all, I'm just briefing that what is exactly the laser, and then we'll discuss about the laser beam machining. Okay, so laser is nothing but the light amplification of stimulated emission of radiation. Okay guys, so it's a kind of light only, or we can say in terms that it's a kind of photon that is generated. Okay, so how this photon is generated, till now we were discussing about the electrons only, but in this case whatever the energy that is transferred in terms of light, that is generated by the photons. Okay, so for this I'm just using these two figures. So first one is like this is, I'm just briefing that this is the nucleus. Okay, and around the nucleus there is a classes is there, like ground class is there, then first class, second class, means upper classes are there. Okay, so means the element which is generating these electrons, for that you can just go and you can just search that how many classes individual elements has, and up to that what level it can fly, or it can transfer. Okay, so I'm just briefing the mechanism here. Okay, or working part we can say. So this is the nucleus. Okay, and this is a first this is the ground class we can say, and this is a higher class, top class we can say. So here this is the electron. Okay, so this electron is moving is every electrons which is moving around this nucleus. Okay, so it is moving in itself only, means itself whatever the classes it has been defined, it is moving with respect in it itself only, means if this is the electron, one electron I am considering first one, so this is the ground class. So it has whatever the energy that has, that is move in the ground class only. Okay, so this is continuously moving in this ground class. Okay, and this is the top class. Okay, so these electrons will go to the second class or the top class, we can say, when it get very small amount of the energy. Okay, is it will get a very small amount of the energy, it will shift it to the second class or the upper class, we can say. Now how this energy they can get, like this is this very small amount of the energy, if they will get, they will shift it. But how this small amount of energy they will get, there are many sources. If there is a vibrations, okay, whatever, like if we are keeping any a laser source, and if we are providing some vibrations, then this electron will shift to the top class. Okay, or like we can say that if we are using the lamps or the light, we can say we are using, then it will shift it to the another class. So if we are providing little amount of the energy, this little amount of the energy can be transferred in any forms. And when it will transfer, like if we are creating small vibrations, then or light we are providing, then this is as it is is it was moving in ground class, it will shift it to the upper class. From here it will move toward the upper class. Okay, is to retain in the upper class, it again needs some kind of energy, because obviously at ground level there is a different amount of the energy is required. If it will move to the first class or higher class, then there is a separate energy, means more energy is required to maintain in this class, that it can rotate. Okay, so when it will this is the one electron which is in the ground class, just we are providing a small amount of the vibration or light, we can say. So it is shifted to the, as it is rotating, and by rotation only it is shifted to the first class. So for that, to retain in the first class, to maintain its own level in the first class, it needs some energy. But whatever the energy we have given to it, it just go to the first class and again come to the ground level. Okay, so when it will come to the ground level, it dissipates the photons. Okay, it releases the photons, we can say, in other words. Okay, so it releases the photon, and again it will come to the ground class and it's rotate again. As I saying that again it will we are providing some vibrations, again it is lifted to the second class, and this will reach over here. Again the same thing, same formula, same concept, that if it do not have the energy, means whatever the amount that has to retain up to there, like we can say like 1 second, 2 second, 3 seconds, so up to that it will sustain there. But after that again it will come to the original class, so again it will releases the photons. Okay, so this is the story of one electron. Now I'm just taking it to the two electrons. So these are the two electrons, okay, which is moving in this direction. Okay, so as it is moving in this direction, we are just disturbing them, we are providing some vibrations, so they will be shifted to the upper class. Okay, again if whatever the energy that have sustain up to in the second class or upper class, we can say, so it will be there, and again it will come to the its original classes or ground class, we can say. So when it will come to the original class, it will releases the photons. Okay, so if these are the two electrons, then it will releases the two photons. So this is basically the concept, to generate the light. Okay, these photons are nothing but the light only. Okay, so this is the light amplification of stimulated emission of radiation. Okay, this is the meaning of these photons. Okay, so here this is I'm using this is the example of Rubik crystal. Okay, this is the example of Rubik crystal we are using. So this is like we can say like a prismatic section is there, tube, we can say. So in which these are the electrons. Okay, these electrons are at ground level right now. Okay, and we are using both the sides, we are using the reflectors. Okay, this is the like we can say like it is partially visible. Okay, it is, so whatever the energy that we are providing, it will be transferred to the electrons, so that's why we are using this will be partially visible. Okay, and these two sides, top and the bottom side, we are using the reflectors. So reflectors are like, this is a reflector, this is a reflector. Okay, so this is a reflector means, this is if like, I do not have exact thing, but for an example, like if this is a glass, like if this is a glass, then this is the top portion of there. Okay, means this is the kind of glass, inside there is electrons are there, okay, at the ground level, and at the top of this we are using the reflector. Okay, now this reflecting is this portion, okay, not outside, this portion is reflector. Okay, so this is like whatever the energy, and okay, so this is like whenever like we are this energy is transferred to these by electrons, it will try to move here and there. Okay, and as well it will gain the energy, so it will try to move to the upper class. So basically they kinetic energy is increases, and they will try to collide here and there. Okay, so whatever the photons, when these photons is releases, okay, photons is releases, they are colliding with this surface. So this is a 100% reflector, this is a 100% reflector. So what will happen that they will basically reflect these electrons, okay, in this direction. And here we are using this another one, that is a partial reflector. Partial reflector, why it is partial reflector? Because we want to release these electrons from this area, from this side. Okay, so this is a small hole we are using over here. So from this small hole, these energies, these energy this photons, okay, which has a very high energy, they basically releases. So is like, this is a very small hole, and whatever these photons, those who are coming from in this direction, if they are unable to transfer at the same time, if they are unable to pass from this hole, they will basically collide with this surface. So this is a partial reflector, so again it will reflect it. So when it will reflect single, I'm just, let's assume that single photon is there. So when it will completely reflect from here, so there is another photon which is coming in this direction, so it will collide with them, and again it will move in this direction. Okay, so this is basically the process. Okay, so let's discuss the working part of it. So this is the ruby crystal we are using. Okay, these are the ruby crystal. Okay, and these are basically the lamps. This is, and this is one is the lamps. Lamps means the light through which the generate light is generated. And as I said, that that is a glass kind of things, but glass is basically the cylinder. Cylinder is also we can use, but here I mentioned that that's a kind of uh, rectangle cross section throughout. Okay, so this is lamp we are using. So initially these are these photons, sorry, these electrons are at ground state. As you will supply switch on this lamps, okay, the you will supply the power. So power supplies is on, so this lamp will be on, turn on. Okay, and as the light will on, this light will transfer to inside. Okay, so whatever the electrons which is at the ground state, they will basically get high energy. Okay, and they will try to move in the high classes, okay, top classes. And again this energy is kind of like for some time only. So they basically releases the photons. Okay, these photons are releases by these individual uh, electrons. Okay, and as this photon is releases, the again this electron will come to the ground state. As the lamp is continuously on, so again it will go to the first class, again it will come to the ground state. So this process will happen, and they are generating the photons. Okay, so these photons, as I said, that we are using this hole over here. So whatever these photons, they are passing through this hole, and they are making a beam. Okay, now this is the workpiece, this is a kind of workpiece. Okay, so from which we have to remove the material. So this is the kind of material that is removed, and we are giving the feed to the workpiece. So this workpiece is moving in this direction, and this is a red line, is basically this is a through which the material has been removed, okay, from the workpiece area. So whatever the kind of machining is required, we can perform, or whatever the shape is required, we can produce by this one. Okay, so this is a working process of this laser beam machining. Okay, now I'm just briefing that what are these lasers, and I'm not going into that much detail because that is already available in the books. So you can, for that you can prefer the PN Rao. Okay, so I'm just briefing these two types of the electron lasers basically we have. So first is the solid state laser, and second is the gas laser. Okay, for the gas laser, first one, that's like different types of the gases are there, like CO2 gas is there, argon is there, neon is there, a mixture of helium and neon is there. Okay, so these gases we can use. So when you will provide means a kind of laser beam is laser kind of tubes is already available in which these ionized gas is filled. Okay, these are basically the ionized gas. So ionized gas means when these has a ions, means positive ions or negative ions, electrons here we are I am talking about, I want to say. Okay, so when you will provide the energy, they basically uh, electrons which leads to the higher position, that's same that we discussed. Okay, next is the solid state lasers. Okay, so if we are talking about the solid state lasers, then there are three types of the lasers are available. Okay, so first is the Rubik crystals that I discussed just before few in the last slide. So that is basically made up of the chromium and the aluminum. Okay, and that has a wavelength of very small, that is in the range of zero point 0.7 microns. Okay, next is solid state laser is Nd:YAG. Okay, that is in the range of 1.06 micron in wavelength. Okay, so here is Nd is basically the neodymium. Okay, Y is basically the yttrium. Okay, A basically is the aluminium, A represents the aluminium, and G represent the garnet. Okay, so this is the solid state laser that is made up of the Nd:YAG, and that is in the range of 1.06 micron, that is in the wavelength. Okay, and similarly, like a neodymium glass laser is also available, so that is in the range of 1.64 micron. Okay, so that depends that what kind of wavelength we require, because okay, so that is in the range of that, that depends on what kind of wavelength is required. Accordingly we are using these lasers. Okay, so just I'm taking few of the two problems that has been asked previously in the gate examinations. First one in the PI in 04. So here the you have to match the list one, with the list two. In the list one, it is mentioned the materials. Okay, and the list one machining processes. Okay, select the correct answer using the codes. Okay, so this is the materials and this is the machining processes. So what are the materials that we are using? That is a machining of the conductive material. Okay, and ruby road, electrolyte, and the abrasive slurry. Here processes are the ECM, EDM, USM, and the LBM. So let's start with the recent one that we studied today about the laser beam. So what is best suitable, which material we are using? That ruby crystal. Okay, so if we are talking about the LBM, that's laser beam machining, then ruby crystal is we are using over there. Okay, if we are talking about, like, after that we study about the yesterday we discuss about the ultrasonic machining. So ultrasonic in the in which we discuss about the abrasive slurry. Abrasive slurry means we are using the water or any kind of chemicals, we can say, along with the abrasive particles. So that is by this one. Okay, next one is the electrolyte. Okay, so electrolyte we are using okay, let's see on the basis of these two. So first one, like if we say like D, in D is 3, so this is option is available, this option is available, so either A or either B, either A or B. Okay, let's go for a B option. B, for B it's 4. Okay, so for B it's 4, so option only C is available. Okay, in B it's 2, means for the ruby crystal we are not using in the EDM process. So let's, on the basis of this one, we can say for the electrolyte we are using the ECM process, and EC is basically electrochemical machining, in which we are using the electrolyte only. Okay, that we discussed that ion is generated into that. And the electric discharge machining, so this electric discharge only be occur when the material is conductive. Okay, means the tool and the workpiece both are conductive. Okay, so there only the arc is generated. So this is the for the for A it is 2, and for C it is 1. Okay, so the option will be C is correct. Okay, let's move to the next one. So this is also, this question was asked in uh, gate PI in 2005. Okay, so machining processes, in the machining list one, there is a machining processes are there. In the list two, it is the operating medium, that in which medium we have to operate. So these are like abrasive jet machining, electron beam, electrochemical, and EDM process. Mediums are dielectric, electrolyte, abrasive slurry, vacuum, and the air. Okay, so let's discuss first one, that is the abrasive jet machining. So for this dielectric, no need for that, no need for electrolyte, no need for vacuum. Okay, so abrasive slurry and the air we can say. But guys, as the I discussed that abrasive slurry is generally is termed like when we are using some kind of chemical along with the slurry or water we can say. But in the abrasive jet, if we are talking about the abrasive water jet machining, that time we can say that we are using the abrasive slurry. Or if we are talking about the ultrasonic machining, that time we can say that we are using the abrasive slurry. But if we are talking about the abrasive only, then from whatever the options is given to us, in which that is only air is suitable. Okay, next is we are using the electron beam machining. So for the electron beam machining, the vacuum is required. Without vacuum, we cannot generate the electrons. Okay, so this is required. This electrochemical machining. Electrochemical machining, we have to use the electrolyte. Okay, and for the EDM process, means electric discharge machining, we have to use the dielectric medium. Okay, so let's see. For A, it's 5. So for A, it's 5, and there is only one option. So option A is correct. But let's see other options are available or not. So for B, it's 4. So B is 4, and for C, it is 2. C is 2, and D for it is 1. Okay, so thank you so much, guys, for this session. Okay,